Let's get into this, shall we? Number 11. A particle is confined to a one-dimensional box. The ends of the box are slowly moving towards the middle. By slowly, we mean that the end speeds are small when compared to the speed of the particle. Solve for the Lagrangian formulation and then using the Hamiltonian. If the momentum of the particle is p naught, then when the walls are a distance x naught apart, find the momentum of the particle at any later time, assuming that the collisions are of the wall are perfectly elastic. Also assume that the motion is non-relativistic at all times, and when the walls are a distance x apart, the average external force must be applied to keep each wall moving at a constant speed. What is it? So I had trouble visualizing this problem, so I wrote a program. This is kind of what I did. It's not that much coding. Basically, I'm using VPython, and let's run this sucker and see what it does. Alright, so we've got a particle moving, then it hits the wall, and I have it graphing the velocity, and this is the magnitude of the velocity, so it's only going to be a positive version. And what we've got is it kind of gets a velocity bump. The walls are moving at 1 meter per second, as you can see here. The velocity of the walls are moving at 1 meter per second, and the initial velocity of the ball starts off at 25, and then it just kind of gets bumped up every single time it hits the wall. There we go. To me, this looks exponential, but I can't really tell until I pull it over to a spreadsheet file and see what we can do with that. So let's let this thing run. Whoa, there we go. Alright, we created our graph. I have it spitting out a CSV file, so that way we can kind of see what's going on. Let's open up Ping Pong. Sorry, it's taking a while. Give me a second. Hold on. Patience. There we go. Over the years, I've become less and less patient with this thing. Alright, so it's got a 25 meters per second. It's going to hang out there for kind of a while, and then it's jumping up to 26, and 27, 28, 29, 30, 31, 32, 33, and then it jumps up pretty fast from there. Every interval at some point, it just kind of goes, there we go. Every single instant is changing. In fact, it kind of changes. Does it change double? No, it doesn't really do it, because I have the time interval between these things as 0.0005 seconds. So that's pretty quick. All right. You know what I'm going to do is, instead of massaging it here, I'm going to open up this file right here. Whoa, no, this isn't the one I wanted. Oh, I guess I didn't save it. Oops. Actually, you know what? I had to have saved it. Give me a second. Hold on, let me find it. There we go. This has got to be it. Oh, I get it. I understand what I did wrong. I saved it as a different kind of file. Alright, give me a second. I'm going to pause the video. Alright, so here's my data. I fixed it up a little bit while I put it on pause. Basically, here's what we got. I've got the time, and what I did is I actually took this over here and I applied a filter, and then I basically said, give me all of the different numbers. And so here's all the different numbers at the specific times that they hit. And I want you also to kind of graph a exponential function for me to see how it compares. And when I look at it, it kind of does not compare at all. And that saddens me, because I don't know what this blue line is, the actual data that I pulled off of the Python file. And the green line is what an exponential looks like, and that would be e to the power of, what did I say it was? I don't know. I think it was I think I had the equation 25 times e to the 0.465 times t, and apparently that's the best I could do to match it up, and it didn't really match. So I want to see what function I can do that kind of gets steeper like that. So anyway, that's where I'm at.